Okay. Hello, everyone. I'd like to present the second presentation that I gave at University of Maryland. It's about selection bias. Okay, so here's the overview. So we have a sample, and a sample supposed to be representative of the population. Well, that's not always true if the sample is not really a random sample from the population. In this case, bias estimator might be biased. So here's one example. We should compare two groups, case group and control group, y equals 1 and equals 0. And why this could be like a cancer, right? So in this case, a simple random sampling may not have enough observations for y equals 1 to get efficient estimation. So among the, like, suppose you have a 1,000 sample, but the case group is only 5%, then you only have a very small 5% or 50, right? So that's not really enough. So in that case, we probably want to do something better. And so outcome-dependent two-phase sampling structure is that we have a two-phase structure where phase one, we have a random sample of big, large sample scale survey, and then random sample, and then observe y first. And then phase two, using the y, observe the y values to stratify the sample and allocate the second phase. So like suppose we have a 10K, and then among 10K we get only 5% is like a 5K, 500, and then 9,500, y equal 1 and y equal 0, and then we just select the 500 all, but from 9,500 we get another 500. So then we get 1,000 sample size in the final sample with the equal 50-50 case, right? So that's probably better than having 50 to 950. So which one do you prefer, right? I mean, so this is the better situation. Another example is like in this paper, you have 154 cases with partial missing. So among the 154, you have only 19 cases that observed everything. So then you only observe, you only have 12% of the complete observation, and everything else you have a partial response. So if you use the complete case only, so that is the CC analysis, then you will have a large standard error. So for example, if you compare this, if the ML analysis, maximum likelihood analysis uses the full information, so you have a quite efficiency loss, right? In this case. Another example 3, length biased sampling. So here's suppose this is a kind of a toy example where you have a distribution of school families. So the level is a family level table, while the second table is a children level, person level table. Okay, so this is a family level and school level for the same population. So for example, you have for example, in this particular town, you have a 5K or 5,000 families with 4 children. So then in terms of children, you have a 20K, right? Because 5 times 4 is 20. So that's basic idea. Then the distribution, family level distribution is different from the children level distribution. And of course, family level proportion of those owing home is different from the children level families owing home. So if you are interested in the family level estimate. So what you are really interested in is the estimating the proportion of families with homeowners. But if you use a student to estimate all these parameters, then you will get inherent bias. So that is basically a length bias sampling problem. So in example 1, missingness is planned to reduce the cost and improve the estimation efficiency, and it is sometimes called planned missingness. Example 2 is the true response mechanism is unknown. Example 3, the selection bias is implicit due to the nature of the nature of the length bias sample. Okay, problem setup. So you have a model, and then you observe x and y only when delta equal to 1. Then you have a sample. Okay. And you can classify this missing data problem into 2 classes. One is type A, type B. Type A, you observe x and y only for delta equal to 1. So that is a bias sample problem. Example 2, we have a partial information. So you have some missing data, partial missing data. So this is a typical missing data problem. Example 3 can also classify it into type A problem. So in this setup, what we want to do is to make some reasonable model assumption and then do estimation. So we need 2 models. One is the model about y. The other one is model about delta. And model about y is called outcome model, population model, or process model. While model about delta is called the selection probability model or propensity score model. So we will go ahead and assume that this outcome model will follow the statistical model with a finite dimensional parameter theta, while the selection probability model is assumed to be known, which is not always the case, but we'll just assume it for now. So known selection probability assumption may not be realistic for type B problems, but it is still a good starting place for discussion. So I'm going to first go ahead and discuss the type A problem estimation method for type A problem. So starting point is to use the Base Theorem. So if you use Base Theorem and develop the model for the sampled part. So this is the conditional distribution of the model for y given x among those sampled, right? And then using the Bayes theorem, we get this form, and then this is actually pi xy. So we can write it in this form. So like a weighted form of density. So this is the density that we're gonna use to the likelihood function. So we can call it conditional likelihood. So it's conditional on the sample, right? Conditional on the sample. So we can call it conditional likelihood. Sometimes it is called the sample likelihood. So conditional likelihood approach, once you have the likelihood, right? Once you have this likelihood, you can take the log and then construct the score function, things like that. So you can take the log to get the log likelihood and then solve this equation. So this is a score function, which can be written as something like this. So you can see that this is the usual score function, and then you subtract something, right? You subtract something conditional on delta equal to 1. So the second term can be called the bias correction term for the score function because of the selection bias. Okay. First remark is that if this is a kind of MAR, missing and random type. So if the response mechanism depend on X only, then this is the same Bayes theorem. First Bayes. Second one is it doesn't depend on X, so Y, so you can get rid of Y dependence, and then this can go outside the integration, right? Because it doesn't depend on Y. And then if you take and then it basically cancels. And so then the denominator is just density function. So if you take the integration, it's equal to 1. Equal to 1. So that means the propensity score function can be safely ignored under this assumption. And which means that the bias term, this term is 0. Bias correction term is 0. And that is essentially the missing a random condition of Rubin. Example 1. So in the case control study, the propensity score function depends on y only. So we can write it this way. So then you have something like this, right? So that means the Base theorem. So this is basically property originally pi xy, but now you have a x disappears and y is just a binary. So either 1 or 0. So you have a 1, 0, and so you get one numerator, 1 or 0. That's it. Interesting part is that you have the same denominator. So if you take the ratio, then the same denominator, so they cancel to each other, so that you end up getting this form. So that is the ratio is a kind of odd. So conditional odd of event y equal to 1 in the sample is this form. So that means, so this part is the, okay. So then interesting part is that this is the also odd in the population level, conditional odd in the population. This is the conditional odd in the sample population. And then you have a constant term. So that means this, if your logistic original outcome model is a logistic regression, so if this is this one, then this is just the ratio. So if you take the, basically, if you put this constant term into the log, into the exponential function, then you need to take the log, right? So that's why you get this form. So what's the message? The main message is that if you look at if you compare these two other functions, one is the population level, the other one is the sample level, you get the same slope. Even though sampling is biased, you have a biased sample, it doesn't have any effect to the slope part. Only the intercept changes, but usually we are more, we care more about the slope part, not intercept part. And so that means you save a lot of, I mean, you get a lot of efficiency gain if you use the length biased sample. I mean, if you use case control sample, because you have more sample size to cases. So and so this is a better strategy. Example 3, length biased sample is more tricky because the propensity score function may depend on other variable, say z, that is not in the outcome model. So suppose this is the known function of like a sampling weight. Suppose this is the known function of z, then we can apply the conditional likelihood method using the following two-step procedure. So step 1, we compute the conditional expectation of the propensity score function, right? The conditional expectation. And then now this pi tilde is now function of x and y. So once you get pi tilde, then you can obtain the same conditional likelihood, right? And so that is the main idea. But how to compute this conditional? So step 1, how to compute this conditional expectation? You need some property identity which comes from the this paper, that Pepperman and Shibachkov paper. So that means what? Well, so the main point is that this guy, so expectation of W given X and Y and delta equal to 1. That means what? That is the weight model. So that is the conditional expectation of your weight. Weight is the inverse of the propensity. Weight give as using the covariate nx and y among the sample. So remember that in the sample we observe everything. We observe x and y and w, everything. So conceptually we should be able to estimate this conditional expectation. So this part is more difficult because it's a population level. So population level, the problem is that if the sampling, because of the sampling, the distribution of the population level is not equal to the distribution in the sample level. Okay, so computing this guy is difficult, but using this relationship, we can use a sample level. So this is a sample level. So we can use the sample level model to construct the weight model in the sample, and then take the inverse to get the population level estimator, which is a pi tilde, right? Pi tilde here. So can be obtained from here. Okay. And for this, this weight model, there's some. Okay, we can use some beta regression model to make a model for pi, and then the inverse of the weight model, you can use the beta prime distribution. So you can derive this, but so there's some details. I'm not. I think this is not really beyond the scope of this presentation, so I will just skip a part. But if you are interested, you can read this. Okay, so here's a summary. Weight model setup. Weight model step. Use the observed values of W and XY in the sample to fit a weight model in the sample level. Okay, so that's this model, and then using the estimator plugin to get pi tilde using this relationship, and then pi tilde can be used to construct the conditional likelihood function. Okay, and then you maximize it with respect to zeta. So that's a way to adjust for the selection bias in the type A sample. Okay. Type B problem. We have a partial information. So we want to incorporate that. And in this case, EM algorithm can be typically used under some simplifying assumption. So on the complete response, if there's no missing data, we'll just use this, right? And now, but because we don't observe, if we don't observe Y for delta equal to 0, then we need to, so for delta equal to 0, we don't observe that, then we need to compute the conditional expectation. That is the E step, using the current parameter value. So then you can see that you have a Q1. So this is can be called Q1. This can be called Q2. And evaluated zeta t. And M step, update the parameter by finding the maximizer of this guy. But interesting. Okay, but let me just continue. So first remark is that in missing and random, so on the missing and random, we have a pi xy equal to pi x. So in this case, x cancels because it's a function of x only. So you get just this one. So then the Q2, so I'm looking at this Q2 term. The Q2 term, you can now ignore this part because of missing a random. And then the maximizer of this guy is actually same thing, using some Jensen's inequalities. I have a proof. So that means what? That means your Q2 term. So if you remember that this Q1 and Q2, right? So the maximizer of Q2 term doesn't update. So we don't have any update for the second component of Q. So it doesn't really contribute because it doesn't really have information. So which means that we can, the second term of the Q does not contribute to the parameter estimation of zeta. So that means we only use Q1. So that this is Q1. But Q1 doesn't depend on zeta t, right? Because it's just a doesn't depend on zeta t. So it's just this term. Okay. So basically that means what? That means under missing on random, we can just use complete case analysis. That's it. Okay. Here's some application, interesting application. So suppose you have a data integration problem. Suppose you want to combine two surveys. You have X and Y1 and Y2. X is a demographic variable and Y1 is health variable and Y2 is a social economic variable. A survey A, health related survey, observe X and Y1. Survey B, social economic survey, observe X and Y2. But you are interested in fitting the regression of Y1 on X and Y2. So in this problem, that's not easy, right? Because you don't have a joint observation. Classical approach is to use X. So we want to create Y1 for the each element sample B by finding a statistical twin from the sample A. And the statistical twin is based on the X information. And that is based on this conditional independence assumption. And that is a little bit misleading. I wrote some reason. Basically, you use this assumption to create the imputation, and then now later you use it to analyze it. Then you are kind of messing up the data. Okay. So proposal is, so this is the data structure. So you need to specify two model, right? Joint model Y1 and Y2. Then you have two parameters. So Y1, the relationship Y1 to X, you can use this sample A. For this one, you cannot really sample 2 because you don't observe Y1. But you can still apply EM algorithm as long as the sample model is identified. So that is, you can compute so you have a log likelihood for zeta 1, zeta 2, compute it as a conditional expectation, and M step you update it by maximizing with respect to zeta 1, zeta 2, something like that. Okay. Well, I think there's a so this is pretty much a standard EM algorithm. And then once you have a parameter estimation, then you can use that to predict. So basically you can predict Y2 using this distribution because you have everything observed. And sample B, you want to predict Y1 from X and Y2, right? So then you can use the Base Theorem. And you have all the parameters. And there's some issues about the model identification. The idea is, okay, if you specify the joint model something like this, then you plug in to here, right? Plugging into here to simplify, you get something like this. So then you have how many parameters? 1, 2, 3, 4, 5 parameter. So you have 5 parameters, but you only have how many? intercept x and y bar xy, right? xy2 covariance. So and y, well, so problem is that if you do that, okay, right. So you can only identify these, but not the joint. That is different. This because this is all the information you have. So different parameter values can construct the same model. So if you do that, you cannot really identify the model. So this is not really identifiable model. But if you include the quadratic term, then you now can obtain so quadratic term. Then you have basically I see. Sorry, I should have. Let me back up. So alpha is no problem. You can always estimate parameter alpha because you observe x and y1. You observe x and y1. So parameter alpha is no problem. So this is known. You can treat it as a known. So only these three are unknown. So you have a 3 unknown parameter, but you have a 2, right? So you have only intercept. I mean the linear term, and you cannot really estimate the 3 parameters, right? But if you have a quadratic term, then you now have 3 parameters with the 3 terms. So that's how you can estimate the parameter. Okay. So this is the paper regarding discussing this problem. So conclusion, take home message. So type A, missing selection bias, is more like a unit-line sparse. Type B, we have a partial missing data. 2 models. Model on delta, we can call it propensity score model. Model on Y, it can be called the outcome model. We assume that propensity score model is known. Outcome model is unknown with unknown parameter theta. And type A, we can use conditional likelihood method. Type B, we can use EM algorithm. Okay. I think that's all. Thank you very much.